Imagine traveling across the universe in the blink of an eye. Picture yourself moving from one galaxy to another, not in years or centuries but in mere moments. Vast distances, measured in light years, could be traversed in mere seconds. The concept of light years, which currently defines the vastness of our universe, would become almost irrelevant. This is the tantalizing promise of wormholes, theoretical tunnels that could connect distant points in space-time. Imagine a tunnel that bends the fabric of reality, creating a bridge between two far-flung corners of the cosmos. While seemingly the stuff of science fiction, wormholes are firmly rooted in the realm of scientific possibility, thanks to Einstein's theory of general relativity. These equations suggest that space-time can be warped and twisted, potentially allowing for shortcuts through the universe. For centuries, humans have gazed at the stars, dreaming of reaching out and touching the cosmos. The night sky has always been a source of wonder and inspiration, sparking our imagination and driving our quest for knowledge. But the vast distances between stars and galaxies seemed insurmountable. The sheer scale of the universe has always been a daunting barrier to our dreams of interstellar travel. The speed of light, the universe's ultimate speed limit, presented an impenetrable barrier. According to our current understanding of physics, nothing can travel faster than light, making journeys to even the nearest stars a multi-year endeavor. Even reaching our closest stellar neighbor, Proxima Centauri, would take over 4 years traveling at the speed of light. This immense distance highlights the challenges we face in exploring the cosmos. Wormholes offer a potential shortcut, a cosmic bypass around the traditional limitations of space and time. By creating a bridge through space-time, wormholes could allow us to leap across the universe in an instant. Instead of traversing the vast distances between stars, a wormhole could connect 2 points in space-time like a cosmic shortcut, allowing travelers to bypass the intervening space altogether. This would revolutionize our approach to space travel, making the impossible possible. This concept, while mind-boggling, emerges from the elegant equations of Einstein's general relativity, which describes gravity not as a force but as the curvature of space-time itself. The idea that space-time can be bent and manipulated opens up a realm of possibilities that were once confined to the pages of science fiction. Imagine a future where advanced spacecraft can navigate these wormholes, embarking on journeys that span the universe in the blink of an eye. This would not only transform our understanding of space travel, but also our place in the cosmos. Scientists and researchers are already delving into the theoretical underpinnings of wormholes, exploring the mathematical and physical principles that could one day make this dream a reality. Their work is pushing the boundaries of our knowledge and challenging our perceptions of what is possible. The formation of a wormhole would involve the distortion of space-time on an unprecedented scale, requiring energies and technologies that are currently beyond our reach. However, the pursuit of this knowledge is driving innovation and inspiring new generations of scientists. As we continue to explore the possibilities of wormholes and instantaneous travel, we are reminded of the boundless potential of human ingenuity and imagination. The dream of traveling across the universe in the blink of an eye may one day become a reality, opening up new frontiers and expanding our horizons beyond anything we can currently conceive. To understand wormholes, we must first grasp the revolutionary concept of space-time. Space-time is a 4-dimensional construct that fuses the 3 dimensions of space with the dimension of time into a single continuum. This concept is fundamental to modern physics and cosmology. Einstein's theory of general relativity, published in 1915, forever changed our understanding of gravity. Before Einstein, gravity was thought to be a force between 2 masses, as described by Isaac Newton. However, Einstein proposed a radical new idea. It proposed that gravity is not a force acting at a distance but rather a consequence of the curvature of space-time. This means that massive objects like stars and planets warp the fabric of space-time around them, creating what we perceive as gravitational attraction. Imagine space-time as a flexible fabric. When you place a heavy object on this fabric, it creates a depression or a dimple. This is a useful analogy to understand how massive objects influence space-time. Massive objects like stars and planets create depressions in this fabric, much like a bowling ball placed on a trampoline. The more massive the object, the deeper the depression it creates. These depressions are what we experience as gravity. Smaller objects, such as planets, moons, and even spacecraft, move along the curves created by these depressions. Smaller objects like spaceships simply follow the curves in space-time created by these massive objects. This is why planets orbit stars and moons orbit planets. They are following the curved paths dictated by the warping of spacetime. Now imagine folding this fabric in half. If you could bring two distant points on the fabric together, you would create a shortcut between them. This fold represents a wormhole, a shortcut connecting two distant points on the fabric and thus, two distant points in spacetime. Wormholes are theoretical passages through spacetime that could create shortcuts for long journeys across the universe. By traveling through the wormhole, one could bypass the vast distances that would normally separate these two locations. This concept, while still theoretical, opens up fascinating possibilities for future space travel and our understanding of the universe. The theoretical foundation for wormholes was laid in 1935 by Albert Einstein, one of the most influential physicists of the 20th century. His groundbreaking work in the field of general relativity revolutionized our understanding of gravity and the fabric of spacetime itself. Alongside him was his colleague Nathan Rosen, a brilliant physicist in his own right. Together they embarked on a journey to explore the deeper implications of Einstein's equations. They discovered a solution to Einstein's equations that described what we now call an Einstein-Rosen bridge, a concept that has fascinated scientists and science fiction enthusiasts alike for decades. This theoretical construct is better known as a wormhole. Imagine a tunnel-like structure that could connect two separate points in the universe, allowing for instantaneous travel between them. This solution suggested the possibility of a tunnel-like structure connecting two different regions of spacetime. Such a bridge could, in theory, enable travel across vast cosmic distances in a fraction of the time it would normally take. Just like a bridge over a river, this bridge could allow for travel between these distant points without traversing the space in between. This idea has profound implications for our understanding of the universe and the potential for interstellar travel. However, the Einstein-Rosen bridge, as originally conceived, presented significant challenges. The most pressing issue was its inherent instability. For one, it was highly unstable. Theoretical models showed that the structure of the wormhole would collapse almost instantaneously. The throat of the wormhole, the passage connecting the two distant regions, would collapse faster than light could travel through it, making it impassable. This rapid collapse rendered the wormhole useless for practical travel. Furthermore, the existence of such a bridge seemed to violate certain fundamental principles of physics. One of the most critical issues was the potential violation of causality. Causality is the idea that cause must always precede effect. If a wormhole allowed for faster-than-light travel, it could theoretically enable time travel, leading to paradoxes and inconsistencies in the timeline. This would challenge our very understanding of the nature of reality and the laws that govern it. Despite these challenges, the concept of the Einstein-Rosen bridge has continued to inspire physicists and researchers. Modern theories and advancements in quantum mechanics and general relativity are constantly pushing the boundaries of what we know, keeping the dream of traversing the cosmos alive. While we may not yet have the technology or understanding to create stable wormholes, the pursuit of this knowledge drives innovation and exploration. The Einstein-Rosen bridge remains a symbol of humanity's unending quest to unlock the mysteries of the universe. The instability of wormholes, as predicted by Einstein and Rosen, posed a significant hurdle to their potential existence. However, later research suggested a possible solution: exotic matter. Exotic matter, unlike the ordinary matter we are familiar with, possesses negative mass and negative pressure. While we have never observed exotic matter in the universe, its existence is allowed by certain interpretations of quantum physics. If exotic matter exists, it could, theoretically, be used to prop open the throat of a wormhole, preventing its collapse and making it traversable. The negative pressure of exotic matter would counteract the inward pull of gravity, creating a stable passage through space-time. The concept of exotic matter remains highly speculative. However, its potential role in stabilizing wormholes highlights the intricate connection between the fabric of space-time, the nature of matter, and the possibility of cosmic shortcuts.